Yeah.
All right, let's get started with this session. In introducing Russ on Monday, I mentioned that he's come and give a presentation or a lecture at every one of the NeuroHackadamies that we had. And there's only one more person who's done that, and that's JB, who's been in every single NeuroHackademy, and sit band, apparently the NeuroHackademy in Seattle in summer, and has provided really useful perspectives and taught people really useful things every single time. And I think this is a new perspective that we'll hear here that's related closely to the research that JB does, that I think addresses some of the issues, say, that Russ brought up and issues that we're thinking about. And I'm very excited to hear it. So thanks, JB, for being here.
No, thank you. Thank you again for the invitation. I will try to talk, but as Arya said, first of all, it's fantastic to be here. Thanks. And second, I will try to talk about analytical flexibility, and that's related to some of what Russ talked about a little bit, but we'll also try to show you a couple of tools that we've developed in the lab that address to some extent some of those problems. And I hope to make that conversation and be interrupted and on all those things. Yeah, so this is the plan. In the middle of it, there should be a little survey, and I want to ask people how they choose their pipeline, and see if you can take a few minutes to. If you go in that tiny URL. You can already, if you're bored by the talk, you can already start the survey if you want. I'd be very interested to see what are the response. And I will, if that is a good survey and you find it useful, or we discussing it, we find interesting things about it. I might actually make it a much more wide, worldwide survey for the neuroimaging community. Anyway, let's start with some. I think a couple of definitions that haven't yet been in the talks, if I'm not mistaken. We talk about the reproducibility. That's one of the big part of the problem that we are.
Can I interrupt you? If you do something with that, can you go and kind of?
If you go to more, you can actually.
Oh, more.
Can I hide it?
Hide.
Oh, thank you. So just as a remember, if you haven't heard those terms, we usually talk about reproducibility in the smallest sense as something that when you try to reproduce your own work with your own data, own pipelines. But we also talk, and this is the definition of the data science in London. We talk about replicability when you take the same methods and try to get the same results with another data set, with another cohort. And robustness when on the same cohort, same data set, you're trying to find the same result with another method, with another pipeline. So in general, that's the interesting aspect, of course, is how much any results that you get is generalizable and in what context that result can be generalized. And that's the thing that is really hard to assess. And what often you get the title of the paper to be very general, but the actual methods and things are much less general. And knowing when things are still true is difficult, if they are. One of the first thing I want to show is this, just rehearsing a bit what you heard and learned before. This is the famous Brian Nosek paper on reproducibility of psychology, and that's and all the red dots here are kind of all the dots are replication of an experiment in psychology, usually a reaction time kind of experiment, and all the dots that are in red are showing the effects that are less than the effects. Sorry, all the dots that are below this line of this diagonal are showing an effect that is less than the published effect, but the red dots are also not significant. And that's just to remember that this is there's a big problem. We don't know whether it comes from effect size and that's what we've seen. You've seen that before, the size of those little cohorts. The effect size is on the y-axis. The size of the little cohort shows the size of the sample. We don't know if that's an effect size problem, and sometimes it is. All the replication of the second paper, by the way, were have a higher number of subjects than the original ones. But In this instance, you have like this effect size that is sometimes a bit too high because it's a the winner effect problem. But going down to almost zero for this link between BDNF and hippocampal volume. But we don't know also if there's not something which is in the pipeline or like viability of the pipeline. And one of the things that I don't think we heard yet is the p-hacking problem. And some of that is probably due to p-hacking. So who heard about p-hacking? So I think a third of you may not have heard. So that's interesting. So p-hacking is the usually well-intended system where you have to find some results on some data sets. You do an ANOVA, it doesn't work. You add another covariable or you add an interaction term, you redo the ANOVA and so on and so on. And because you have worked on the same data set and not on an external data set before testing the effect on a new data set as in a machine learning kind of framework. Because you've done that, you have increased the risk of error by a factor of a known factor, but sometimes very large number. And that's a very famous p-hacking thing. And when you look at the results in the literature, I love that thing because it's just so funny to look at. Look at the p-values or the z-value equivalently in the literature, you find that big gap of a non-published thing. So estimating the effect sizes of any effect is going through that, and maybe there's some aspect of reporting, of course, but there's also aspect of the file draw effect when non-significant results are not published or less published. So that all those things are kind of also part of the pipeline problems. What kind of methods and pipelines do I want to put on the data before I can get some results? Again, you've seen that slide before, and just remember, this is the fact that you find higher accuracy in finding, in discriminating between, say, patient and healthy controls. So you find a higher prediction. A better prediction when you have smaller sample size across many different cohorts here. So that's very so the question is, why do we find, if we have a proper cross-validation framework, now we've gone through the machine learning kind of courses, if you have a proper cross-validation framework and you actually are testing on another data set, how come you get that result, and what is the reason of that result? It's not, I think there's partly, I think the answer is that mostly, with small data sets, people may try more things than with big data sets. And therefore, there's a kind of possibly a higher, flexible, analytical flexibility in small data set than in larger data set. If you have a really big data set and you have to do a lot of things, you're unlikely to try 10 or 20 different things. Well, if you have a smaller one. So this may be due to, first of all, a broken cross-validation framework aspect. So you have a cross-validation, but you're not testing on a completely independent data set. So that's one aspect of that result, but also the fact that there's an interaction with the size of the cohort here that I think is particularly interesting. So that's just as a thought, and if you have another explanation, please go and because I'm still trying to find out whether that's the right explanation for that result. In my own lab, there's Jaume Docas, when he was a postdoc at the time, looked at the UK Biobank and how to predict whether people were smokers, not smoker, or smoking or not smoking, or and look at different cohorts, and say if you learn on a specific cohort whether you can predict some characteristic of a subject, how is that prediction going to pan out if you try on another set of data? So we look at like a young versus old, and you learn on those young, for instance, you try to predict on the older adults, and you find that those predictions go down very quickly. But the other thing that happens in that paper is that he looked at at different learners, simple learners like SVC, or more complex learners, and that there is an interaction as well with the size of the cohort and the complex learners. So choosing those things, choosing your kind of pipeline here was also critical for those results. You've learned about the naps. Russ detailed that in a lot. What I want to emphasize in the nap experiment is that the only reason why there's so much variability, and even within as Russ described, even within those results that are quite close to each other, right? The T-map were correlated. I mean, not sometimes very highly correlated, maybe 0.6, 0.7, 0.5, but still correlated. Even in that sort of space, there's a highly variable results in the publication because of the thresholding aspect and the statistical thresholding aspect. But the thing is that no one in that paper, the thing I want to emphasize here is that no one had the same pipeline. They all did something different with the same data. And I think that's the critical thing that I want to discuss here. You just heard, and I will come back to the data. Actually, we'll do that right now, but soon. But before, still on the functional data, this is another experiment by Alex Boring, Camille, and Tom. We looked at, the same data set with 3 different very well established pipelines or processing framework. And you look at the differences and you find that, there are massive differences so the image might look a little bit the same. But then if you look at the thresholded and the results in the region of interest and all those things, then you get super high variability. And this is like a plot showing the average t-statistic across 2 pipelines or 2 processing framework versus the difference of the t-statistic on the y-axis. And you see that difference is very high wherever you are on the x-axis almost. This is an old paper. I love that paper. It's interesting, especially I was actually did during my postdoc work a bit on those methods. This is a paper called the cluster failure paper. I don't know if you heard of that. It's a cluster. It was a test actually. I had the idea at the time, you threshold an image, you look at the size of the blob that you get above the threshold, and you think, okay, if that size is too big, then it's unlikely to be noise. Noise should not give you such a big size of a cluster. And what happened? So there were good theory and things and beautiful mathematics actually to being developed to actually test for those things. So what Eklund did was to take non-activation data, so like a resting state data, put that in the test of those tests with different framework like FSL, SPM, and so on, and then look at whether you find more false positive than you should, like with a fake sort of activation paradigm, and it did. There's a lot. And the problem here, it was not actually really the pipeline. After studying carefully those things, I think my conclusion at least is that it's not really the pipeline itself or the framework itself. Both SPM, SPSL, and FNU have visible statistical methods. It was the parametrization of that cluster test. So FSL had a very low threshold by default, and who's going to change that default? In real life. While SPM had a very high threshold, 0.01 versus 0.001, like in p-value kind of a thing, and with low threshold, the theory that was implemented was definitely not correct and was failing miserably. So I think that's an interesting kind of a paper describing that. In the lab more recently, we worked on looking at different functional connectivity, dynamical functional connectivity methods, and there's plenty of methods to actually assess dynamical functional connectivity in fMRI or other. And we took the 7 most used method. We implemented them, making sure that they work and so on, and then look at the variability of the results that you get when you take those 7 things. What's the variability across those pipelines compared to the variability of the actual dynamical functional connectivity across time, for instance, or across subjects, so comparing the methodological variability to the biological variability, and you find that and this is the plot that you see on the left, and have a look at the paper if you want more of the details. But basically, you find that this is almost to one. So there's almost much variance in the biological aspect than in the method aspect. And there's more work to be done on that, especially why and so on. But I think that's also like a bit of a wake-up call. So you had this great talk by Serge this morning on the diffusion. Actually, Maxime, Descoto, and a lot of people, I'm sure including Serge, try to do this, the NAPS experiment using diffusion data. So get one data set of the diffusion data set, send it to, I'm sure you participated in that. No, maybe not. I'm sure, okay, you should. But take that one data set, send that to 50 labs, and look at what kind of a track you get back after all those choices that you've seen this morning, like, what preprocessing, what denoising, what model, what ODF model, what, and so on and so on. And you find, very different kind of and I'm sure for the trackometry aspect, there will be variation on that due to those differences. One of the very worrying and sort of almost like, okay, oh my God, what are we doing here? Kind of a question I had is when I saw those results with Erin Dickey, and I think Dave Kennedy was involved in that study. When you look at the size of the left caudate, for instance, that's the cingulate, the size of the left cingulate, and you look at those estimation across different segmentation tools. And that's the difference between, and you see that there's very little actually correlation. The correlation between ants and free surfer is really poor. Like, it's a 0.4, 0.5 correlation. You think, okay, so across subjects, that size, the size of that structure is really not estimated the same way. And there are many reasons for that, and maybe some of them are good, but it's just the reality is that we don't have the same results with those two tools. Nikki Bagwat in my lab actually went that further and look at what are the connectome across subjects, connectome, and you find very different kind of a connectome across subjects, like how subjects structure are correlated across each other, and that's very different connectome. And this one is interesting. It's because there's in this tool there's a sort of there's a prior on the symmetry of the brain that is not in the other tool, and that's why you find a much more symmetric thing. And that has impact on the actual result. Like, this is a study we're looking at the size of the brain, of some of the brain structure, brain matter, and so on. Whether across between autistic kids and controls, and you find that sometimes you find a difference when you have with one tool, and you don't find the difference with another tool. And I think that's the reality of our life. But but the question is, what do we do in practice? Another aspect which I'd like to just touch upon, because I think it was a discovery at the time when we saw that as well, is Tristan's work on the numerical noise aspect. So this specific experiment was let's try to segment the brain, the gray matter and white matter with I think it was free surfer in this instance, and actually FSL. And then let's try to segment that brain on one cluster, one HTTP cluster, using a container that's, so we know exactly what is the version of the software and the environment of the software, and the library environment of the software, and so on. And let's try to do that on another cluster and see what is the difference between the results. So same data, same container, same pipeline, same tool, and we find and they found different those all those little voxels that are different after the difference between those two things. So so first of all, who knows what is a container here? I hope everyone. Not everyone. maybe that's another topic. It's a topic for like, I'm sure there might be some information on that later in the week. But anyway, container is a way of making sure that all the environment and libraries and dependency of the software are the same and are packaged in one container in one place, so that you can transport those things into onto different computers and get the same environment and same pipeline. And in this case, the problem is that those containers still call for a lower library on the operating system, and those lower libraries depend on the version of the operating system. And that's what caused the difference in the slight difference in the numerical noise that is between those two HCPs, so those two clusters. Whether it is important or not is another question. The fact that that has an effect, and which algorithms are actually subject to numerical noise is something that is really super important to know. And what is the effect? So that's what's one of the things that we actually investigated with Tristan and the master students between our two labs. And we looked at for the simple registration, like a linear registration of the brand to a template. What if you introduce some numerical noise? So what you do is, it's a very neat thing. You just flip the last bit of the least impactful bit of a float operation, for instance. And you look at what's the impact of just adding a little noise in that. So it's a very tiny amount of noise. It's in the 32 would be minus 32 10 to minus 32 or something, or maybe not 27, whatever. But someone will know that better. But basically, there's very little noise introduced, and you still see that those registrations. So we looked at the frame displacement. And we see that for some of those registration, noisy registration, and even the normal one is noisy, right? It's not like introducing specific noise. It's like the normal thing that is happening. You see that the registration, frame displacement registration is maybe of the order of 1 millimeter sometimes in some subjects, in some cases, and on average is 0.2 millimeters, something like that. So, and the standard deviation here is shown. So it depends on the scan. It depends on thing, but you do have a fairly bit of noise in just the linear registration, which should be so SPM for interesting reasons has much less noise, and we think that's because it has more prior on things of how they do things. Or maybe there's other reasons so tracking down which algorithms are kind of subject to noise, and sometimes they can noise can increase with the number of operations you're doing. So that is also a little bit of a unknown thing and an interesting thing to look at. I think I will skip this one. This is just to show that if you take an example, an algorithm, so this is optimization algorithm for machine learning techniques, and if you take those algorithms and you just try to re-implement those things, you have massive, despite the fact that it's the same pseudocode and same algorithm, you have massive effect of the implementation. So I just pointing that to you. I want to go a little bit in the real life experiment that was done between Tristan, my lab, and Madeleine Sharp labs, where we looked at and just looking at again thinking of the pipeline variation aspect, but in general sense. This is the example of 11 papers that we try to reproduce or replicate using and we see that it was super hard actually to get not only the data, so the data was one thing, but also the analysis pipeline. That's the thing I want to point out here. If you don't get from the paper the actual exact pipeline with a container, things like that, it's almost impossible to do a pipeline just from the description of a PDF. It's just you have too many choices. You don't know what to choose, and you don't have the time to choose all the options to get to the result. So I think I will skip the other ones, but basically this experiment taught us that never ever publish something without publishing the code and publishing the data again, because that was like a miserable experience to try to get those things right. And the last little things, like in terms of reproduction, we did a study a while back on essential tremor, looking at how and taking a meta-analysis of essential tremor results and the implication of the cerebellum in essential tremor, and we looked at whether those results were going to be reproduced with like a larger cohort and a new data set and a larger control cohort and so on. The reason and the thing we did was because we had that analytical flexibility problem in mind. We said, okay, we're going to do the most classic and the segmentation that are being kind of done all the time using the classical tools and like things. And we're going to say that there is a result if there's consensus across those very classic, very well-established pipelines. And we couldn't find any consensus in that. So technically speaking, we couldn't replicate things, although some of the pipelines show some of those, a little bit of some results of the initial meta-analysis, and some didn't. And so I think I want to emphasize that this is not like the kind of a new pipeline that has not been well tested and so on. Those are the pipelines that are being used and being cited hundreds of thousands of times, in the publication. I think that's the problem that I'm. So I think there's a paradigm shift a little bit in the data sense of things. There's also I guess there should be like so paradigm shift in the sense that went from the small local data to to the very large UK Biobank or ADNI or all those very big data sets that we could download. Less and less they are downloadable anymore, and more those things have to be processed where they are, and that's also the case for smaller data set as well. We encountered more and more people say, we're not actually able, especially if you are in Europe with under GDPR, you're not able to actually move data to the US anymore easily. So human data, I mean. So there's a paradigm shift that I think there's a shift to big data, but also a shift to a local data. And I think that's something that is happening. That we have to, I mean, it's not going to be 100%, but there's a trend in that direction for sometimes good and bad reasons, but that's definitely a trend. Yeah, and from silo data to in the same way, I think there's a trend now to that sees that those variation in pipelines are kind of at least a question mark at least. So I think there's a couple of things that, first of all, it's only in the case where you don't know what's the ground truth. If you know what's the ground truth, that's kind of easy. Like if you know that your loss function is to predict, like a disease versus not disease, or to that is not a problem. But if you're trying to find, the correlation with the with some biological effect that is measured by neuroimaging, you don't usually have the ground truth, and this is where analytical flexibility is really a problem. And and you have to think, okay, I've tested and I've measured with this tool. What if I had chosen something else? So it matters when we don't know the ground truth, and that's usually the case. So what can we do? I want to pause a little bit on that, but because that's one possibility is to be search and to know all the details of the diffusion pipelines and know exactly on what data the right pipeline is, and to be a world expert in that, and and basically being super knowledgeable in all the things that you're doing. That'd be lovely. I don't think that's completely possible, but that'd be lovely. I mean, I would love a world where we know exactly, we are really expert in everything that we do. That's probably not going to happen. So one way, and I think the way I would advocate is to use various pipelines and check the robustness of the results with various pipelines that are supposed to do about the same things, but have been implemented by different groups and things. And that's not easy either. Like, I'm not minimizing the problems of that, but that's at least a workable and possible solution. And it's great to see when things are confirmed, and that's fantastic. And it's also interesting to see if they're not, and we can actually report that. If you are in a machine learning framework and you have results of many pipelines on the same thing. So let's say I have different ways of measuring gray matter thickness or something like you can actually use all those features and think, okay, those are just other features from another pipeline. And maybe will be some redundancy, maybe there will be less redundancy, but at least you can treat that as a more more features to actually predict something. Okay, and that's great, but that's when you are in the case of a machine learning framework where you use those things as predicting features, but that's not always the case. There is always the capacity to say, okay, I'm going to publish what I find with those things, and eventually in the literature there's going to be some kind of meta-analysis across those data sets, those methods, and we're going to eventually converge to something that is true. It's a bit of a longer process. It's a bit less satisfying at individual level as well, I think. But that's one way. I think that's partly how we progress at the moment. Those things are things that are confirmed or not. But also it means that people are trying to confirm things, which is not as much as we do at the moment. There should be more on that, I think. There's also methods, Jeremy and Camille in particular, and with Tom, I've been trying to say, okay, if you have many results on the same data set, what are the statistical methods that you can use to do some consensus analysis across those things? So those methods exist and emerge, and they're useful. I think that's one possibility. There's also, at a more fundamental level, choosing the pipelines and not only assessing, but making sure that the pipeline you're using is something that is super well established, I think is also a good way. And of course, it might depend on the data, so you might still have some kind of expertise to have and all those things, but that is a normal way, So I will talk a bit more enigma on things, but having exactly the same pipeline and that has been battle tested on many data sets is a good thing in general. And there are efforts in the community to make those things happen. And I think we should join those efforts and make sure that yeah. So this is the time when you work, I rest, and if we could take like 5 minutes to fill that little tiny URL survey. So it's called the tiny URL neuroimaging pipeline. Neuroimaging pipeline. So please take a few minutes, and I will ask everyone to do that if possible. And then when you're done, I don't know, maybe we can have a thumbs up on Slack or someone. I don't know, there's a Slack a channel probably for the lecture. So if you could just put a thumbs up on Slack, on the Slack channel for the survey, and then so I'll leave you a few minutes. And I go get coffee and be back, and then no, just checking. And please ask questions or anything meanwhile, I think it's kind of wasting time. And the survey was, it's a first attempt and really my question is, when we choose a pipeline, what rationale do we use? And I think that's it's not as easy as so please go over the whole thing and I promise to put the results on Slack, so that. The submit doesn't work? Oh, that's terrible. That is a terrible situation. Let me check what's going on. There's already 7 responses though.
There's a copy responder link at the top. Yeah. Oh, we're doing preview mode.
Oh, I'm sorry. I put the wrong link. You're doing preview mode.
Yeah, but Kendrick already posted the right link.
Oh, okay. Kendrick, thanks so much.
Use Kendrick's link.
Okay. That is the thing you shouldn't do late at night. If you go on the Slack, Kendrick has put the right link.
Oh, there's a right.
Yeah, I'm sorry for that. I don't know. I think I made that tiny URL and then made it again, but didn't change it.
No. Which channel are you? This one.
Three, 5. All right, so maybe a few more people to get 30. Yeah. That's the, I mean, sorry, it was my fault. There's a new link in the lecture channel that is the right one. I'm so sorry. The other link.
If you go to the Poline Nipoppy channel in Slack, there's a link there that will work. Okay.
Apologies for that.
The one sent by Kendrick.
Yes. Yeah.
Right. So 33 responses already. So get maybe another 30 seconds and then we'll move on. Okay, cool. Very cool. Okay, I think we should reach 42 just for the sake of what. All right, thanks. Please finish the survey when at your leisure. Like, I think again, the reason of that survey is, and maybe I can have a quick show of hands. Reason of that survey is my prior is that we don't choose the pipelines because of our own test and making sure that they work on our own data most of the time. Most of the time, I think we choose the pipelines just because the lab is using that pipeline. It has been using it for 5-10 years, or or because someone is knowledgeable in that pipeline, or because it's easy to install, or because it's very well used across the literature or things like that. But I think we have the choice of the pipelines that we're using for processing, for estimating those variables, and is probably not, you know, like a very scientific one. It's more like a logistical one. So I think that's my prior. I want to see if that's true, and I will let you know the results. I think, you know, it's yeah. But you know, I like for the story. I mean, I had a student who was, you know, doing this kind of work, and okay, we're finding different results with our hippocampi volume between, like, you know, FSL and free surfer and things like that. And I had colleagues to say, okay, but that's the wrong way of, I mean, this is wrong. Like, the thing that we want to have is the true pipeline that does the right thing. I don't know how you choose that pipeline that does the right thing. That's the problem. I mean, I understand their perspective. That's a very, like, you know, like but you know, but the sociological aspect of our work is that we are, you know, using those things because they come and, you know, someone else have done that, and, like, you know, and yeah. All right, so so one of the things I want to talk about in the next phase of that lecture is the some of the new informatics platform that we've been involved in developing in the lab. To sort of like, you know, try to answer some of the problems that I've talked briefly about. And before I go into, like, what are those tools and what they can be useful for, I want also to say that, you know, there's when you embark in doing those kind of platform-ish sort of work, you have to think carefully of how you want to do it and what you want to do. There's the implementation aspect, which requires a lot of you know, expertise in software engineering, and that's I think that's a good thing, because it means that, you know, people that are going through those things can get jobs almost you know, like outside of academia, which is important. So, but that's you know, that's you know, having all the good development practices that partly you learn here at NeuroHackademy is really important. There's the sustainability aspect of and how those projects are, you know, like, if you start to, you know, release some of those things. I mean, Serge was saying, you know, we don't have to support that. You just, like, you know, you can use, and, you know, without. I think me, when I start to, like, you know, start some of those projects, I very have in mind the way I can make those things long term, because I think that's where they're useful, and also that's a little bit of a, you know, like if you're, you know, proposing something, I mean, I do feel like there's some kind of responsibility of making sure that they go on, you know, and so that's the sustainability of those things is important. I also think that, and that's partly linked to the sustainability aspect, that those things have to have some kind of distributed governance. Like, you know, I'm sure DIPI have many labs that are contributing. Those labs have their say in where DIPI goes, and, you know, contributors to DIPI have their say. It's kind of like, you know, the duocracy aspect of those projects is really important. And also, I don't think that building the tools themselves is, I mean, this is really cool and this is great, but building, you know, like, and training communities and students and researchers to use those things such that there is better science done is also, so building community of practices around those tools is something that I think is critical. So there are many, I mean, not that many actually. There are quite a few infrastructure or projects that would help you assess analytical flexibility. And I had a student in the lab actually do review of those things. And there's a number of and it's a bit of a complex landscape. You know, it depends on the operating system, depends on the tool dependencies, depends on the choice of the pipeline itself and processing. There's the parameterization of those tools. All those things will impact results, and all those things might be useful to actually have tools to actually assess those things, right? So that's what Jacob has been doing, and in that landscape. Numerical stability, the workflow engines, continuous integration techniques, container manager, and data provenance aspect, you know, all those computational environments and so on, web computing. All those things can be at some stage, useful aspect of that can be used for like, assessing analytical flexibility. So we did a bit of a, like looking at all those tools that exist and can be helpful. And it's interesting. There are, like not that many that are really, sound, but you can definitely use NeuroDesk or Brain Life or other things, and that will help you in that sphere. They're in different kind of a space and things, but if you study those things, I think that's and choosing one of those things to help you to assess analytical flexibility is one of the things that I would like to push forward. In my own lab, we did a bit of, we did some of the projects, and I want to go on at least one project, and at some stage, I think Michelle hopefully will join us on Zoom and will demonstrate the Nipoppy project. But I want to go through those things and explain a bit what they are and why we've been developing those and what they could be useful for. So we've worked on basically on two major kind of project and tools. NeuroBagel is so the current paradigm at the moment, as I said, is that there are large centralized databases for data. So data is really like the heart of the thing. Like if you have enough data, a lot of the not only better sensitivity and better statistical power, but a lot of the problems that we have, like in the non-reproducibility aspect of the researcher, will be resolved. So some of them, at least some of them. So the current paradigm with the large centralized databases, where often you download like those 30,000, 40,000 subjects from the UKB and so on. That's with a unique legal and ethical framework, and that's kind of a problem. Is have some issues. It's getting very expensive. Sustainability is always a question. Like part of the reason why the UKB now you can't download the data, but you have to go on their research platform that they have. Like you have to pay them. You have to pay the company that is doing that, such that is sustainable. So sustainability is an issue for those things. It's very hard to change anything for those massive things. Computation is a problem, and interoperability is like even if you are on you have like UK biobank, but you want to check on another data set and things, fusing those data sets is going to be a massive problem. Okay, so like merging those data sets is going to take so much time, so much effort. So the paradigm shift that hopefully is that we can have like distributed infrastructure where not only the population bias is reduced, but also the ethical and governance aspect stay local to the tool to the centers. And one of the things that calls for is a local environment where processing and pipelines can be run in the same way. So so a lot of the things that are rely in our community rely on the brain imaging data structure. The brain imaging data structure, I guess everyone knows what it is. Can you raise your hand if you don't know what it is? Okay, cool. Oh, you don't? Sort of?
I know, I thought you said no.
Okay, cool. Okay, so a lot of that has now completely taken over the neuroimaging community. I mean, not completely, but largely taken. The problem, I guess one of the issues that is that the set of metadata associated with the data set is still very poor in some ways. It's still better than nothing. It's a very but it's a kind of a minimal thing in some sense. So if you look at, for instance, the participant.tsv files of the Open Neuro dataset, and you look at what is in this participant.tsv file, then you find that there is the participant ID, but you find like age with a small a, and then age with a big A, and then you got sex with a small s, and sex with a big S, and then you've got handedness, but also if you look at all those things with a hand, for instance. You get what is the handedness columns, for instance, or the hand. You've got all those values, right? And that's so even if you take the infrastructure that is probably the best well maintained and created in some ways, because everything is in bits, everything has been validated by the bits validator in OpenEuro. Even if you get that, you go on the data set and you're trying to co-analyze data set from different, because you want to co-analyze different data sets from OpenEuro, you will find all those problems and others. I'm just taking that example. So harmonization of the terms and what is there is a problem that has not been resolved even with bits. Bits has resolved a lot of things. So one thing that we've worked on, when I say we, like it's Seb Hirsch and his team, is to look at those TSV files or those Excel spreadsheets and try to harmonize, have a data model and basically say, hey, if you have DX in that column, what do you mean? And have a little tools to say, hey, I meant diagnosis. And if I have group and 0, 1, 3, like whatever, what do you mean? And so having a way to say, hey, this is Parkinson, this is PAT in that column of that Excel spreadsheet means actually Parkinson's disease. Is really something that is missing if you want to start to co-analyze things that are distributed around the world. So there's a little tool to actually help you do that. It's a web tool, so the data don't move at all. It goes through, you go through your TSV or CSV file, and then you kind of annotate those things with a common data model that is, and that makes things. Now you can start to think, okay, I have now described properly what is this column and what are the values. So the values, if I have 0 in the sex column, if I have 0, 1, I have to map and say, okay, 0 is male, 1 is female, 2 is whatever, and so on. And what that thing does is to actually just create, you have a data dictionary in bits sometimes. I mean, most of the people and most of us actually don't feel that data dictionary, but it exists. There's a JSON file where you can describe your column names and whatever. But that's for you human. What that thing does is that it adds to that dictionary some actually proper computer readable annotation that can describe exactly what is the diagnosis, what is the sex, what is the handleness, and so on. So it just complements the human data dictionary with a computer oriented data dictionary. And that makes it feasible to actually have those annotation at different instances of different places, and therefore being able to actually search across those places with exactly the same terms where you know exactly what you're talking about. So that's the NeuroBagel query. So if you go on the query.neurobagel.org, you will, it's a public thing to try it, and you will actually be able to say, okay, age from 50 to 70, and then search across those nodes, and we have the moment 4 or 5 public nodes just to show things. But in particular, we have the OpenEuro public node where you can search the MRI, for instance, across all those data sets after harmonization of those information, which I think is important. And so maybe I can show you. I don't know if I have a. Yeah, I have a. And that's how it looks like. So maybe I'm looking for minimum age of 50 or 40, whatever. Maximum of 60, and then female, and then maybe I want at least a T1 weighted image. And then, I can have a submitted query on that. It's going to look and go across all those nodes, and those nodes, they are, and it's going to find, things that are, have some data sets. I'm a bit surprised that there's so few of those, but anyways. So those are the nodes that are being queried at the moment on in the public node of NeuroBagel. So yeah, so that is actually to answer the problem of I actually need a larger cohort with some correct, so with those exact things, and I want to search both OpenEuro, and I want to search Indie, and I want to search another data set, or and so on. And then sometimes you may have access to the data because OpenNeuro has the CC0, and sometimes you may not. Okay, and that will depend on the data set. But you will find, like in this instance, 14 subjects over 28 that have those characteristics in that data set. So, and if you look at, if you go on OpenNeuro itself, you will see that, OpenNeuro is actually, you have a link or say, hey, search OpenNeuro with NeuroBagel because those things are harmonized. OpenNeuro is not by default. I will skip that. This is the technical way this is done. So it's a Sparkle query that goes into those little nodes. And also, I think the important aspect is that all the governance of those things are being local. I think that's skip that. I want to switch to another aspect of those infrastructure, which is the locally. How do you compute your pipeline on a local data set? And that's also be useful. But if we want to move to like a decentralized way of doing things in neuroimaging, I think one of the reasons that is going to be useful is that we would have exactly the same way, the same pipeline, the same container can be launched for different data sets, and that's again with the aspect that those pipelines may have to be adapted sometimes, but so Nipoppy is kind of the second thing that we've worked on that, and it was advertised in the title, which is it's basically it was developed by Nikhil Bawat and Michel Wang and others in the lab, and now like many outside of the lab. And it's basically the idea is like if you have a bit specification for a data set, what is the specification for a neuroimaging study? And a neuroimaging study would have much more than a data set. Like they would have not only a neuroimaging data set, which would be a bits data set, but you would have all the tabular data of the assessment that have been maybe connected, like on the red cap thing, or they would have like so this Nipoppy is really the both a specification but also protocol to say, hey, you have to start from there, and this is what with experience we think that this is a good way of organizing your study, and this is a good way so you have tools now to bitsify, but you may and so on. So this is really like it's both a package, of course, it's also like a training environment, and it's also again a bit study sort of specification aspect, right? And actually it is now merging with bit study. So there's work that we're doing with the bits community to make sure that this is one specification. So Nipoppy is not Nipoppy specification; it's a bit study specification, and Nipoppy is just a tool that is helping you work with that specification. So introducing Nipoppy framework. I'm guessing that Michel is online now, so maybe it should be better than me doing that, but I will go through that anyways. So it's about organizing things and doing and guiding people to do things, and rather than starting from where do I start, you have now a guide of how to do a neuroimaging study. So starting from the capture aspect to the curation aspects and bitsification, to how do you launch processing or pre-processing pipelines, how do you curate the status of those things, when do they fail, when do they succeed, how do you extract when you have done your pre-processing and things, how do you extract the actual values of interesting things that you will be using for your analysis, and then how do you analyze things in the end. So it's kind of a kind of a broad framework, but we'll help you follow the track on the whole neuroimaging pipeline aspect. So from the raw scanner to the imaging derived phenotype is really and also give you little tools to help you with okay, this is a tool to see what has been done and processed and what has not, and so on. So again, specification of the study, software package, and the community of practice. As I said, this is really the thing that we want to do. So typical Nipoppy workflow, you do init. It would help you by saying, okay, you're initting some study. I will create those directories for you, and then there will be like a couple of configuration files that you have to edit yourself. You have to be able to open an editor and edit those things. But I think it's reasonable. And then it will help you reorganize your diagrams if you have messy diagram things. We'll have a way of helping you with that thing. And then we'll propose a couple of bidification tool. So you don't have to stick with one. You can use the one you prefer, or what the one that is best for your study. And then you would install. I mean, this is not something like you can install pipelines from Zenodo and say, okay, I want now to run fMRI prep. So Nipoppy install fMRI prep, and then you'll see that in the demo. And then you can Nipoppy run things, and then once you've run, they look at okay, what has been done and what has failed, what has not failed. For some reason, not all processing will run on all the subjects, and that's a common problem. So that's what the Nipoppy track is doing. Is like defining little functions to help you and say, hey, if things have run, this is what I should get out on the disk, right? And so all those little functions, all those kind of helpers, if you want, like to help you progress in the study. And then put the derivative where they should be. And this is, for instance, an Nipoppy dashboard. I think Michel will demonstrate that. And those two, NeuroBagel and Nipoppy, kind of are independent projects, but they can help each other. You can actually query in NeuroBagel if what subjects have been processed with what pipeline, for instance. So those kind of interaction are useful. So takeaway, so it's a local data management helper and pipeline helper, like a launching helper. It really helps in terms of reproducing exactly the same pipeline on like 6 months after or 2 years after. When you are some PhD student, you've done your PhD, and then another student's come in and has to redo the same thing on another data set, or or longitudinally or whatever. So that's really it saves a huge amount of time at the end. It's an investment. You have to invest in it and learn the tools, but then the payoff is really really interesting. So that's the adoption. That's people, collaborators we're working with, and then I just skip that. So that's Michel has a bit more time for the demo. What's the time? Yeah, I will. Okay, let me see if Michel is online, and we can. And basically, I wanted to show that we're using it to do some distributed machine learning, such that you know that you have exactly the same pipeline that have been run on like different places, and now it's much easier to learn from those different results across sites. Yeah, so that's the conclusion. And before I give it to Michel, I think standard and community of practice is one of the key messages. If you get only one thing out of that talk, remember, if you can join and build like a community of practice and around a specification or a standard, that is a good thing that will really help the community and as a whole to like move on. Be sustainable for those projects, like you build things that are cheap, build other things that are not locking syndrome. So for instance, if you are thinking of using a tool that you have to have a license for, or you have to make sure that there's someone who's paid for maintaining all those things, that is potentially a locking syndrome. I think where you can't get out of that because that's not something you can work. Let's say it's a database, and at the end, the person that knew how to maintain the database is gone, and you have all the data there. You have no idea how to get those things back, and all that. So locking syndrome is a problem. So whenever you invest in a tool, make sure that that tool is flexible and open and doesn't kind of lock you in things, right? So I think that definitely is a characteristic of Nipoppy and NeuroBagel as well. Transparent distributed governance aspect of the project is important. Working with the incentive, make sure that we have We love what we do. We get credit for what we do. Sometimes we need to have money to maintain things, and also we have to comply with things. So that are the Carol global incentives that I like to remind folks on. Yeah, so let's move to the. So I'll introduce Michelle. Is a senior PhD student in the lab. Michelle, are you online? And can you?
Yes, can you hear
Yes,
me?
you are online. Let me put you. I make that big. Yeah, I can make big. Yeah. So I'll let you do a little demo, and I'll be here. I mean, I've done the demo myself yesterday, or actually this morning. So I know it works. But we can like have a more like a discussion on why Nipoppy is interesting, or might or where it should be going, like with the room. And so we have like a 20-minute for your demo if you want, Michelle.
Yes, I sent a request to share my screen because you're
The
already
question is,
sharing.
can we
so
hear you
so if
properly? Just a sec, we can't hear you properly yet. Let's try this.
Can you speak now, Michelle?
hello,
Oh,
Yes.
yeah, I can hear
Can
you.
you hear me?
Want to share your screen?
it says someone else is sharing.
Oh, that would be me.
Yeah.
How do I not share?
Share it again and then stop sharing. Let's see what happens.
Share again, and then stop sharing.
I think it's now like my screen tab at the top. This is
Oh, your screen. Yeah, you gotta close down. How about now?
Yes, I think now it should work.
That is my screen too. It's new.
Yeah, it changes like every.
Okay. Can you see the VS Code window?
It's a bit small. I think
Yeah, I can
some people see it. I
increase.
think I would recommend that you join the Zoom as well, because you can see on your screen much better than you will see on the big screen, probably.
On the window, it's gonna be full screen.
So there's a suggestion to put yourself into full screen, or me.
JB, you'll need to do something so that she's full screen and naturally like that.
I think if you click the view button in the other right, it might.
Oh, view up on top.
View on the top.
And then
Side by side speaker.
Shared content. There, there was full screen on the bottom of that place.
Somebody's full screen. I think in the view tab that you were just in, there might be a full screen one.
In the view,
Yeah, bottom.
very
Yeah.
with that one.
and then full screen.
That's better.
I'm just going to reduce Michelle a little bit. And, she doesn't
Sure.
deserve that. So that's a bit better. But again, if you have if you can join the Zoom, which is on Slack, that might. Okay, yeah, it's all yours. Take it away, Michelle.
Okay, so hi everyone. Thank you for having me. I hope you're having a good time at NeuroHackademy. I'm just going to do a quick demo of using Nipoppy to process a bits data set. So Nipoppy is a command line interface that can be installed as a Python package using pip. If you do Nipoppy, for example, -h, it shows like a help text with with all of the commands, some of which we will use today in the demo. So I have some data here that I downloaded from the Open Neuro data repository. Here you have several subjects, and then they all have T1s. So now if I make a new directory called, I think it was demo study, and then change directory into it, and then run Nipoppy init, which JB has shown in his slides previously. All of the commands have this -h thing, and then there's a CLI. I think I'll skip over explaining some of this. But if I already have a bits data, sorry?
Oh, there, you can go ahead. I just muted that.
Okay. So if I already have a bits data set, which is not a requirement, you can create a new Nipoppy project or study, even if you don't have a bits data set, and then there are actually steps in this framework for how to bitsify data, depending on if you have DICOMs directly from the scanner or Nifty files from previous DICOM to Nifty conversion or things like that. But if we start from a bits data set, we can move ahead with the demo because it does some things for us already, which is kind of nice. So here it prints out a bunch of stuff. And now you can see that I had an empty directory. I made an empty directory, but now it created all of what we call the Nipoppy layout. And then there's a bits subdirectory, and it's actually a symlink, a symbolic link to my bits data set that I had in another directory. And then we have containers, derivatives. Most of these are empty or have empty subdirectories. And then there are two files that are kind of important. And JB briefly mentioned them earlier. There's this manifest file and the global config, and we'll touch upon both of them. So if you look at the manifest file, it's a TSV. This was automatically generated because we pointed to an existing bits data set. And so from the bits data set, we can infer which participants and which visits and sessions are in this data set. So here's just a list. But you can imagine that if you start a Nipoppy data set from scratch, then one of the requirements is that you provide or create or have some way to generate this manifest file. And this manifest file, we think of it as like the ground truth of which participants and which visits, and those are not necessarily imaging visits, like they can be for other types of data collection. So which participants and which visits are supposed to exist in this study. And if we know this information, if Nipoppy can know this information, and then with our tools, we can say, we can check which participants and visits out of these have been converted to bits, which ones have not been converted to bits, which ones have run this processing pipeline successfully. So it basically it helps with tracking. And now we also have a command to summarize different tracking statuses. So Nipoppy status, it will print out a table. Right now it's a bit minimal. Here there are some steps that we skipped because we started with bits data directly. So you have one session ID, it's called one pre, 9 participants that are in the manifest and 9 participants are in bits. So basically everyone has been converted to bits, which is like given for our case, but in some cases that's not the case. If you have to do the bits conversion yourself, then this helps, and you can see which participants still remain to be converted. Okay. Now the next step will be to that's okay. Now this demo is for running a processing pipeline on the bits dataset, or multiple processing pipelines.
Michel, can you hear me?
Yes, I can hear you.
Can you just say a bit more on the session versus visit? Because I think that was one of the things that really was a question. Like, you know, it's often a question, and that solution is a good solution, I think.
Sure. So session versus visit. So if you're familiar with bits, then you should know that bits has this concept of subject and also of session, and that is part of most of the bits file names and identifying where what scans are and things like that. So the session is specific to imaging because technically, and bits doesn't really enforce this, but a session is whenever a participant enters and exits a scanner, that is a session. And then if you enter, exit, and then either on the same day or on a different day, go in the scanner again, then that's supposed to be a different session. So that is really what a session is. Whereas visit, we think of more as just, and that's also used more in a bit more, I would say, clinical settings, is you can have participants who come into the research center or the hospital, and that is a visit. And during the visit, you can collect multiple different types of data modalities. Maybe not all of them will be imaging. So then for some studies and for all of the data for some studies, visits and sessions are not always going to match, depending on if it's different people collected different types of data. For example, if you have neuropsychological assessments versus imaging data, usually it's different teams who collect these data. So a lot of times, if visit ID is not very a useful differentiation, then it can be just the same thing as session ID. There's no difference. But for us, it's been very useful to have this extra difference, so that in some studies where it's sometimes a little bit messier, we can have visit IDs that don't match the session IDs for various reasons. Does that make sense? JB, do you want to add things?
No, just perfect. And just to say that, in real life, things are sometimes a bit messy, and that concept of a visit being different from the MRI session is a very useful concept to have. And just thanks, Michelle.
Yeah. All right. So for running a pipeline now, we can do. So JB had previously mentioned this, but all of the Nipoppy pipeline configuration files can be shared through the Zenodo data repository. And then using the CLI, you can search for what is available on Zenodo right now. So for example, if I search fMRI prep, depending on internet connection, it might take more or less time. Here's the result. So we have different versions of fMRI prep. We have also this fMRI prep Siftify, which is a variant that has been developed by one of our collaborators. And then here there is a Zenodo ID. And these you can find if I copy the Zenodo ID, for example, and I go in on Zenodo, and I go to the page for this record ID, then I can see the set of files that will basically be downloaded. And this is what I mean when I say Nipoppy configuration files. It's a series of pretty small JSON files that are required for running a pipeline. Usually they point to a container. So the actual processing environment and container image are not stored in the Zenodo record. So yeah, so then it's just a series of text files, pretty easy to download. So now I can do Nipoppy pipeline install and then paste this Zenodo ID, and it's going to download the files. And then ask me if I want to also download the container. And I say no, because that will take a bit of time. And then there was, I think this was another version that I wanted to get. So here I can install 2 different versions of fMRI prep, basically. And that will work. Yeah. And then it says here also a warning, something update the pipeline variable sections. So here it says open the global config, which is the other file that most likely will need to be modified before being able to run any pipeline. And here, because I have installed FMRPrep, the 2 different versions, they require some additional information that Nipoppy tools by default don't know where those files or directories are going to be. So here I'm just going to paste this here, the free license file, which you need if you want to run FMRPrep, and then also a directory, an empty directory for the template flow templates. And then if you are running this on a lab server, for example, on a lab server, it could be like a shared directory for all of the template flow templates and also the free server license. I don't think that would be best practice to do that. I will also update this path to the containers because in our lab, we have a shared container store where all of the containers that we use are stored together. Again, to avoid, because containers can take a lot of space and we want to share these things if possible. Here I place the container store path. Most of these steps are detailed on the website, which I can also show a bit later. We have a documentation website. Yeah. Okay. So here, I'm not actually going to run FMRPrep in case you were wondering, because that can take a lot of time. So I will just do, but we have this simulate flag. And what that does is basically show you what would be run without actually running it. So the command to run a processing pipeline, which is what FMRPrep is Nipoppy process. And then I say pipeline name is FMRPrep pipeline version, since I have 2 of them, it's 20.2.7, and I only want to do it for 1 participant for now. Although if I omit this participant ID, it's going to run for all of them, and then -- simulate. And before that, I also need to change this to Singularity, because this is a server that doesn't have AppTinner installed. It has an older version, and at that time it was called Singularity. Okay, so it's not the easiest thing to look at on a terminal where a lot of the text has been, where the font size has been increased, but there's also a log file, which might be a little bit easier. So it writes a log file, and here it says simulating pipeline command, and then here is the generated command. So I don't know if you know about containers. This is the container command with all of the bind flags. So it's a bit long because there's a lot of paths to bind and the paths are a bit long. And then at one point there will be the actual FMRPrep command. And I don't know if I will have time, probably don't think I will have time to go over details of how this command is built, but that is related to the configuration files, the JSON things. Feel free to reach out to some of the channels that we have afterwards if you want to learn more about that, because I'm happy to talk about it, but I don't think we have time now. So here are the actual, so here's the container, and then after that are parameters to FMRPrep. So this builds everything, and then it would run it. And we can do the same thing to run the different version of FMRPrep. It would just be the same command, but instead of this version, we put the other one that we previously installed. And it's going to do the same thing. Yeah, and it prints out the command that you can look at. And this is also useful for debugging if something goes wrong. Yeah, okay. So I have previously run FMRPrep, both versions, and I will copy the outputs, or I will remove this. Yeah. Remove the derivatives. And we can look at what's in derivatives is my outputs that I have from a previous run. And now what I'm going to show is tracking, the tracking capability. So if I run Nipoppy status and nothing, oh, okay, I have to delete this thing. Copy this processing status. Okay. I run Nipoppy status, nothing has changed here. We still have the 9 in manifest, 9 in bids, and nothing else. But then if I run Nipoppy track processing, and so I want to run track fMRI prep, and then also with the version, because we have 2 different versions, and it's going to run for all of the participants. And now if I do Nipoppy status again, you see that fMRI prep has completed for 1 participant out of 9. And that is, I expect that because when I ran it, I only ran the first 1 and not all of them for the purposes of this demo. And then I can track again 24.1.1, which is the other version. And I run Nipoppy status and I can see this. So all of this information, these information are found in stored in TSV files inside the data set. So it's nothing really fancy. The way we determine if a pipeline has completed or not is also not very fancy. It's just in the config file. It's in pipelines processing. So when I did Nipoppy pipeline install, it basically downloaded the files and put them in this directory. And there is this tracker file, and then it's just a list of paths with some wildcards for the participant ID and the session ID. And then so here as a user, you can decide basically which paths you consider are the most important, or which paths, the list of paths that such that if all of these paths exist, then I consider that the pipeline has run successfully. So you can be as strict or as loose as you want here. After downloading a pipeline, you can modify this very freely. Same thing for like the runtime parameters. If I don't want to run with the default parameters for fMRI prep, I can go in this other file, which is the invocation file, and change things or add things. But I won't go into too much detail about this. This is using a framework called boutiques, which is pretty useful for what we want to do here. Yeah. So then in my derivatives directory, there is this processing status.tsv. And here is what happens when I run the Nipoppy track processing command. It just writes success or fail for all of these participants. And this file can be downloaded because this is a remote server, but I can download it to my laptop in downloads. And then go on this dashboard, which is publicly accessible. It's at digest.neurobagel.org. And I can upload this dashboard. And it's not really useful for the current status because we already know, I mean, the data set is not very big. And we know that there's only 1 participant that succeeded. And it's very easy to tell who that is. But for larger data sets or in larger multi-session data sets, it can be very useful to have this. This is basically an interactive dashboard of processing statuses. So a summary, snapshot kind of thing. It's similar to the Nipoppy status command, but this is a bit more interactive, and you can do some querying things and then download a subset of this table, for example. Here we have actually preloaded this other data set that we are curating and processing in the lab. And this is taking a bit of time. Okay, not all of the plots have been updated, but this bottom one has been. So here you can see that it's a much larger data set with 271 participants and 2 different sessions. And here we haven't started the processing for the second session yet, which is why everything is fell. But it can be very useful to just have like a snapshot of the status of the processing on the data set. And again, this tracking is possible because we know who is supposed to be in the study from the manifest file, which you can think of as like it's like a flight manifest if you want to know who is supposed to be passenger on this plane or ship or something like that. Yeah, so I think it's time, because I think we said that this was 3 p.m. Seattle time. I have some very brief slides of takeaway summary. So we really think of Nipoppy as a framework that has some tooling, has some specification, and whose overall goal is for trainees to adopt best practices, or to make it easier to adopt best practices, for labs to have more efficiency and consistency in research data management. So when there's like multiple data sets or even a single data set, you don't want it to be processed in different ways, but to have different copies of the data set on different hard drives. And whenever there's new students coming in to kind of redo the whole thing, that's not very efficient. And for bigger institutions to help with eventual data harmonization and discovery. I think JP has shown something a little bit similar to us, but we're working with collaborators and we've had good adoption so far and good feedback also. So if anyone wants to try this thing and also provide feedback, that's very useful because we always are looking for room for improvement. Here's another map with some adoption things for Nipoppy and NeuroBagel. And then finally, as I mentioned before, we have a documentation website, nipoppy.readthetalks.io. There's a lot more information than what I talked about today, although it's still not very complete. We're working on some video tutorials to also help onboard new users. And then finally, we have a Discord community for usage questions. And we're looking for new contributors for the code. So if you're interested in either using or possibly contributing, this is an open source project. Everything is on GitHub in terms of project management and issues and things. We're always looking for new contributors. If you want to try to work on something, say you've contributed to open source scientific software, then please reach out. We have a lot of issues, as you can see, and we have limited time. So any help is appreciated for this. But I think it's also a good experience if you're interested at all in the more developer side of things. We have a good team and working on a lot of different things. So I think I will end here. Yeah.
Yeah, thanks a lot, Michelle. I think that was really cool. Thanks.
Yeah, happy to do the demo. Yeah. And
as Michelle says, like, this is a really good group of people developing that. So if you are interested in joining, like, reach out to the Discord channel. I will put the link to the in the Discord team. Yeah, it's a cool project across a few labs now. Thanks very much for the attention. And yeah.
Diego asks if there's anything we need to take into consideration if we want to run jobs in parallel with Nipoppy.
Oh, that's a good question. There's a HCP kind of arm of Nipoppy that you can actually launch some Slurm. Maybe Michelle, you want to take this one?
Yes. So we have some HPC integration. I don't think we have documentation on it yet, but that's actually something I want to work on like tomorrow. But no, actually, I think I wanted to do that this week. We have HPC support for Slurm and SGE, possibly other things, depending on what your if you have an HPC. Otherwise, if you don't, there are still ways to parallelize things. I don't. There are ways to do it. You can basically, when you run Nipoppy process, you can add. There is a flag of, instead of running the thing, print a list of participants and sessions that need to be run, and then after that, you can use something like GNU Parallel, the tool to parallelize. So we don't have like built-in multi-processing things. Yeah, for various reasons, but that would be a way to do it. But otherwise, HPC support is definitely a thing. For Slurm and SGE, it has mostly been tested on the HPC servers that we have access to. So, but if you would like to try that, I think it would be good to get feedback on whether or not it works for other ones. But it's also very flexible because it's based on a template kind of thing. So yeah, so just, I think there are ways to make it work. Yeah.
Thanks, Michelle. Thanks again for zooming in. I added you to the Slack channel, so if there are more conversations there, you can hear that. What will happen
that's
next
great.
is we have coffee break. After the coffee break, if you're working on the group project, go back to where you were with your Zoom rooms and your collaborators on Zoom. And then if you want to go to the CHN tour, let's meet here, and Kelly will walk with you. Kelly will walk with you to CHN. It's just a 5-minute, 10-minute walk down to campus. So she'll walk with you. Just gather here at 3:30 if you're interested in the tour. Otherwise, you'll continue working on the project. We'll be around to help work on the projects as well, and we'll just go between all the groups. Okay, thanks.
Thanks a lot, Michel. Merci beaucoup.
Thank you.
Good night.